2 மணி ஆயிட்டு ஒன்றும் தொடங்கலையா?
Good afternoon, everyone. So we'll start the program now. On behalf of Marthanam College of Engineering and Technology, it gives me a great pleasure to welcome you all for the final day of our Atal Faculty Development Program on title Advancement and Applications of Smart Materials in Environment and Technologies. We extend our warm greetings to our respected management, principal, heads of departments, faculty colleagues, and all enthusiastic participants who have joined us today with commitment and interest. A very special and heartfelt welcome to our distinguished resource person of this session, Dr. Selvan Bellan, Associate Professor, Niigata University, Japan. We are truly honored to have you with us, and we look forward to gaining valuable insights from your expertise. Now, I invite Mrs. Satyabama, Assistant Professor, Department of Electronics and Communication Engineering, Marthanam College of Engineering and Technology, to formally introduce our resource person to the gathering. Ma'am.
Ma'am, thank you, ma'am. Good afternoon, everyone. It's my privilege to introduce Dr. Selvan Bellan, currently serving as an associate professor in the Faculty of Engineering at Niigata University, Japan. With his distinguished career in thermal energy storage, solar thermal energy conversion, fluid mechanics, and thermochemical reactor, Dr. Bellan has made significant contribution to the field of renewable energy research. He has held prestigious positions across India, Japan, and Europe, including a Marie Curie postdoctoral fellowship at IMDEA Energy, Spain, and has collaborated with leading research institutes worldwide. His outstanding achievement, including over 110 international publications, multiple awards such as Best Research Award from the Heat Transfer Society of Japan and the Excellent Young Researchers Award from Niigata University. Dr. Bellan has also successfully led and contributed to the numerous international government and industry-funded projects advancing technology in solar fuels, hydrogen production, and advanced thermal storage systems. His expertise and dedication continue to shape innovation in sustainable energy solutions. We are truly honored to have you with us today, sir. We warmly welcome you, sir.
Hi, thank you for your kind introduction. So can you hear me?
Yes, sir. Yes, sir.
Yeah, Please give me a second. Let me share my presentation.
Sure.
Yeah. Yeah, can you see my slide?
Yes, sir. It is visible.
Okay. Hi, everyone. Good afternoon. I'm pleased to meet you all through this online meeting. As you know, I'm Selvan from Niigata University. My talk today is going to be focusing on solar thermal energy conversion and fuel production. The outline of the presentation is given here. First, let me give a brief introduction about, concentrated solar power technology and thermal energy storage systems. Then I will present solar receivers and thermochemical reactors we have been developing in our research center, followed by, recent developments of thermal energy storage systems based on sensible, latent, and thermochemical heat storage systems. Okay, so one of the main motivation factors for our research is given here. As you know, climate change and global warming is one of the serious issues in our time. As you can see in this temperature contour, our Earth's average temperature has already increased around 1.1 degrees Celsius compared to 1900. And as you can see here, it is projected to increase up to 4 degrees Celsius more in the next 100 years. For example, here you can compare using this temperature contour, like those who are born in 1950s, what kind of temperature they experienced during their childhood and what kind of temperature they're experiencing now. So these global warming and climate change problems are mainly due to the greenhouse gas emissions into our atmosphere. Uh, as you know, according to current conventional energy production systems, it's very difficult to produce energy without any environmental impact. As you know, in order to produce energy and meet the end use sectors like the residential sector, industrial sector, or for transportation, we have been using gasoline, coal and oil. In this graph, you can see, in recent years, every year we are almost producing more than 35 billion tons of CO2 emissions, right? So we are now in the important phase to, change our energy policy. Otherwise we will have serious consequences in the next 100 years. So to reduce the greenhouse gas emissions, as you may know, International Renewable Energy Agency identified 6 technological avenues. Through them, we can reach the net zero emission goal. The so-called Paris Agreement. Most of the countries signed in this agreement, including Japan. So the strategy is presented here. How can we reduce, more than 35 billion tons of CO2 emissions by 2050? As you can see, 25% of the emissions we can reduce by using renewable energy technologies, and 25% by energy efficiency techniques. So like that, through other technological avenues, how much carbon emissions we can reduce, by hydrogen technology is around 10%. So these are our key research areas. Our research is directly or indirectly contributing to these 3 technological avenues to reach the net zero emission goal by 2050. And these are all our major research activities in recent years. We have been developing, different types of thermal energy storage prototypes, based on latent, sensible, and thermochemical heat storage techniques. And we have been developing some thermochemical reactors as well for syngas and hydrogen production using solar energy. So this slide summarizes, different materials we have been using and different materials we have been developing for all the development of different types of prototypes to utilize solar energy to, produce electricity as well as to produce syngas and hydrogen. Yeah, it may be a little bit confusing to see all these things. So for better understanding, let me give a brief introduction about concentrated solar power technology, how it works, and what are the important components are there, and why we are developing all these prototypes. And let me explain all those things. So let me begin this. Let me give a brief introduction about the concentrated solar power technology. I guess some of you may know about this concentrated solar power. However, let me give a brief introduction for the people who are not aware of this technology. So this technology, converts sunlight into thermal energy first, and then the thermal energy would be used for electricity generation, or the thermal energy would be used for, fuel production. So as you can see, the plant consists of important components like thermal energy storage system, central receiver, heliostats, gas turbine, everything. So let me explain how this plant works. As you can see, this is a central receiver tower, which is surrounded by rings and rings of heliostats. Heliostats are nothing but mirrors, which track the sun's movement throughout the day and reflect the sunlight over the receiver. In such a way, it creates concentrated radiation over the receiver. So as a result, the receiver would be heated up. At the same time, heat transfer fluid, like water or molten salt, it would be pumped to the receiver where it circulates and receives the thermal energy. And then the thermal energy would be transferred to the hot storage tank or it would be supplied to the steam generator to generate steam. It would be supplied to the turbine to generate electricity, and then the electricity would be connected to the grid. This is how CSP plant works. So this is a real plant. It's called the Gamma Solar plant in Spain. And as you can see, to produce 20 megawatt power, it requires huge land. As you can see here, more than 300,000 meter square land is required to produce 20 megawatt power. Right? So this is how solar thermal power plant works. So here, thermal energy storage system, this is one of the important components. As you can see, the sunlight would be converted into thermal energy, and then the thermal energy would be stored in the tank. So, during the daytime, we can convert the sunlight into thermal energy we can store in the tank. And during the nighttime, we can take the hot heat transfer fluid to produce steam and then to produce electricity. So using this component, we can produce electricity 24 hours. Whereas other solar technology, for example, PV system, the photovoltaic, the solar PV panels. So only during daytime, you can produce electricity. At night times, it's difficult. So for that, you need a battery storage system, which is very expensive. So thermal energy storage system is one of the important components. It's one of the integral components of CSP plants. And to improve and to enhance the efficiency and to reduce the thermal energy storage tank cost, we have been developing this kind of packed bed thermocline heat storage system. So for this system, we have been developing and using various sensible heat storage materials, and we have been developing various phase change materials for latent heat storage concept. Similarly, we have been developing various redox materials and perovskites for thermochemical heat storage. So let me present all these systems in the later slides. So this is just a brief introduction where our research is mainly focusing on in CSP components. So this is one of the important component. And another component is solar receiver. So here the concentrated radiation can also be used for syngas or fuel production. So for that, we have been developing various thermochemical reactors, based on two-step water splitting cycles, as shown here. So these reactors convert sunlight into syngas or hydrogen. So for that, initially, the sunlight would be converted into thermal energy, and then the thermal energy would be used for thermochemical processes to produce syngas and hydrogen. So our research is mainly focusing on these two components. For that, we have been developing various prototypes. So let me present them one by one. So let me begin with this, the hydrogen production system. To produce hydrogen using solar energy, there are various solar reactors have been under development by various research centers, by various concepts as well. And our concept is to combine, the beam down optics and the fluidized bed reactors. Can you hear me? Hello? Excuse me, can you hear me? Is everything okay?
Yes, sir.
Can you hear me? Yeah, is everything okay?
Yes, sir.
Okay, yeah. Thank you. Yeah, so our concept is to combine, beam down optics and fluidized bed reactor as schematically shown here. So what is beam down optics? So, in the conventional solar thermal power plants, if we replace the receiver by secondary reflector as shown here, this is a kind of elliptical reflector, so which redirects the concentrated radiation coming towards the tower, so that it creates concentrated radiation close to the ground. So there we can install fluidized bed reactors and we can perform various thermochemical processes. So we have been using cerium oxide for two-step water splitting cycles to produce hydrogen. So our concept is clearly, schematically shown here. So in order to demonstrate this concept, we developed, 100 kilowatt beam down demonstration plant in Miyazaki City, which is here, the south part of Japan. So there, the DNI, the solar installation is very high. So we developed this plant in the south part of Japan. So our institute is here, in the north part of Japan. So here we have a snow during a winter season. So it would break, all the systems during winter season. That's why we developed this plant in the south part of Japan. So using this plant, we can produce 100 kilowatt thermal power, the concentrated radiation. And we developed a fluidized bed reactor. And usually to do experiments, we usually go there by flights and we come back. So it's a very expensive experimental campaign to go there with students and come back. So moreover, to optimize some systems, we need, a steady system. To check reproducibility, we need some constant conditions. So for that, we developed 30 kilowatt solar simulator using xenon arc lamps, so which creates concentrated radiation artificially in lab scale. So as you can see, this is the solar simulator we have in our research center. It consists of 19 xenon arc lamps, which creates concentrated radiation towards the ground. As you can see here, there we put our fluidized bed reactor. So the whole experimental setup, the schematic of the setup is shown here. As you can see, we fill, fine particles. These are all reacting particles inside the reactor. And we fluidize the particles by passing the gas through the inlet, the gas distributor. As you can see, the number of holes in the central axis region of the gas distributor is significantly higher than the annulus region. As a result, it creates a kind of a Gaussian profile, so that the gas velocity, in the central axis region would be higher than the annulus region. So it creates internally circulating fluidized bed. And then using this concentrated radiation, we can, heat up the particles and we can perform the thermochemical, reactions. So using this reactor, we can produce hydrogen. Let me explain how this reactor works. The main concept of this reactor, as you can see, it consists of two steps. The first step is the thermal reduction step. So thermal reduction step is the, dissociation of, metal oxide into lower valence metal oxide. And the second step is the hydrolysis of the reduced metal oxide to produce hydrogen. So, to perform this first step, initially we fill cerium oxide particles inside the reactor, and then we pass the nitrogen gas and fluidize the particles. And after creating this internally circulating fluidized bed, we irradiate the reactor by concentrated radiation. And when the particle reaches around 1300 degrees Celsius or above, this step takes place. As a result, oxygen would be released by the thermal reduction step. And in the same reactor, we usually perform, the second step, the water decomposition step. For that, we control the radiation power. We reduce the power and we switch the inlet gas from nitrogen to steam. And when the particle reaches less than 1000 degrees Celsius, this step takes place, so hydrogen would be released. So this is the main concept of the reactor. So during the first step, we produce oxygen, and during the second step, we produce hydrogen by this step. And here you can see our experimental results. And here you can see what is the central bed temperature as a function of time, and what is the reactor wall temperature, and the gas temperature, and what is the oxygen production rate as a function of time. As you can see, at the end of the first step, we produced around 7 liters of oxygen. And during the second step, as you can see, other details like what is the wall temperature, central bed temperature, and the outlet gas temperature. And this profile shows the hydrogen production rate. So at the end of the second step, we produce around 12 liters of hydrogen. So using 8 kilograms of cerium oxide particles, we produced around 12 liters of hydrogen. And as you may imagine, this reactor involves various processes, various physics and chemical processes. So to understand the system and to improve the performance, we need to get the details of what is the heat transfer, what is the chemical reaction rate, and what is the radiation transfer inside the reactor. So we need all these details. So to obtain all these details, we developed a numerical model, by the combination of computational fluid dynamics, discrete element method, and discrete ordinate radiation model. And this model has been developed based on various assumptions. The flow of the gas phase is simulated from volume averaged Navier-Stokes equations, and the motion of every individual particle inside the bed is tracked by Newton's second law. And the particle collisions are modeled based on the soft sphere method. And based on these, assumptions, the governing equations to predict the gas velocity, you can see, and to track every particle. So we use this equation, and to obtain the particle temperature, we have been solving this equation. And to obtain the radiation distribution throughout the reactor, we have been using discrete ordinate radiation model. So we developed the model, and then to verify and validate the model, we performed experiments for the operating conditions as shown here. And we did simulation as well. So experimentally measured and numerically predicted radiation distribution along the vertical and horizontal planes, in the focal plane, or compared here. As you can see, a reasonable agreement has been made between the simulation and experimental results. And in this graph, you can see, the central bed temperature and the bed, the pressure drop of the bed, what is the gas temperature at the outlet. They have been compared here with, experimental results. And as you can see, a reasonable agreement has been made between experimental and simulation results. So from this model, we can obtain detailed heat and mass transfer and radiation transfer characteristics. As you can see, what is the particle temperature, what is the gas temperature, what is the radiation distribution inside the bed, and what is the gas velocity. So what is the radiation profile? So all these details we can obtain from our model. And based on this concept, and we developed lab scale prototypes, and now we have been upscaling this reactor to pilot and commercial scale. So for that, we got an international project from Australian Renewable Energy Agency. And these are our collaborators, CSIRO Research Center in Australia, Institute of Applied Energy in Japan, and Niigata University. So this is a collaboration research project funded by Australian Renewable Energy Agency. So as I presented in the previous slide, using the lab scale reactor results, we have been upscaling to 300 kilowatt reactor. For that, important operating parameters such as what is the particle size, what is the gas velocity, So what would be the appropriate operating conditions to fluidize the particles, and what is the effect of particle size? So all these things we have been investigating using our numerical model. And this reactor is going to be installed in the 1 megawatt plant in Australia. So this is a CSIRO research center, the pilot plant of CSIRO research center in Newcastle, Australia. So our reactor is going to be installed in this facility. So like that, we have been developing, lab scale prototypes, and we are upscaling these reactors into pilot and commercial scales. And to increase the, efficiency and production rate of hydrogen and oxygen, various metal doped cerium oxides have been developed. So as you can see, or the iron doped cerium oxide, nickel doped cerium oxide, copper doped, similarly manganese doped cerium oxide. Or we have been testing various samples, and as you can see, the effect of the doping percentage. As you can see, if we include 5 mole percentage, 10 mole percentage, or 15 mole percentage. So what is the effect of mole percentage on the performance? So we have been testing different samples, and to test these samples, we have other reactors. Let me present in the later slide. So after preparing the samples, I usually we do XRD. As you can see, these are the XRD patterns of different samples. Different color represents, a different amount of, the metal doping. And as you can see, the series of peaks are due to the fluoride structure. And as you can notice, there are no new peaks due to doping. And it indicates that 5 to 15 mole percentage of iron doped cerium oxide retains the fluoride structure of the cerium-based oxide as single phase. And after synthesizing the materials, to test the materials, usually we take 1 gram of sample and put it in this platinum cup. And to perform the thermal reduction step, I explained the thermal reduction and water decomposition steps in the previous slides. The procedure is pretty much same, but here to test a small amount of sample, we use this kind of reactors, made of, infrared furnace. Usually we take 1 gram of sample, and then for thermal reduction step, we pass nitrogen gas. And when the temperature reaches, more than 1,300 degrees, so in this case, we fixed 1,500 degrees Celsius. So the thermal reduction step takes place. As a result, oxygen would be released, right? So the mixture of oxygen and nitrogen gas would be, collected and using the mass spectrometer, so we can measure what is the oxygen production rate. Similarly, for water decomposition step, so we put 1 gram of sample in this platinum cup. So during the second step, we need to pass nitrogen with steam. So for that, we have this oil bath, distilled water tap setup. As you can see here, we pass nitrogen gas. So the mixture of steam and nitrogen would be supplied to the reactor, and how much hydrogen would be produced, we can calculate using the water displacement method. So like that, using these 2 reactors, we can test the synthesized samples. And here you can see the oxygen and hydrogen production rate with 5 mole percentage of doping agent. For example, manganese, copper, nickel, and iron doped cerium oxides, all samples, 5 mole percentage of doping. So as you can see, what is the oxygen production rate? And this orange line shows the, temperature. As you can see, as soon as it reaches or above 1,000 degrees Celsius, the production rate reaches, the peak level around 90 to 120 micromole per minute. So as you can see, this step is very quick and rapid. So within 5 minutes, the thermal reduction step is done. And in this graph, you can see the water decomposition step for different samples. So the hydrogen production rate rapidly increased around, 200 degrees Celsius and approached zero within 20 minutes. And the peak production rate of undoped ceria in this case is the highest, and hydrogen production of doped ceria continuing for more prolonged period of time in comparison to the undoped cerium oxide. And in this slide, you can see the cycling reactivity of 5 mole percentage of metal doped ceria. And as you can see, the oxygen evaluation is nearly constant level, in all these 6 cycles. So among these samples, 5 mole percentage of ion and copper doped cerium oxide showed a relatively greater oxygen productivity than undoped cerium oxide. And here you can see, the cycling reactivity of 5 mole percentage of metal doped ceria and hydrogen production profiles you can see. And the amount of hydrogen production is around 25% higher for 5 mole percentage of ion and copper doped cerium oxide than the undoped cerium oxide. So these results indicate that 5 mole percentage of ion and copper doped cerium oxide has the greatest stable stoichiometric productivity of oxygen and hydrogen in the thermochemical two-step water splitting cycle. This slide shows the overall, all samples, oxygen and hydrogen production for different amount of doping. This slide shows all, samples like 5 mole percentage of ion, 10 mole percentage of ion, 15 mole percentage of ion. So other materials also. So from 5 to 15 mole percentage of doping. So all results, as you can see, the peak rate of oxygen evaluation rate for iron, cobalt, and manganese doped cerium oxide increased with increase in doping. However, the peak rate of hydrogen production decreases when decreasing the doping. And lower content of a doping agent can favor the overall efficiency of the metal doped cerium oxide thermochemical cycles. That also you can notice, And similarly, we have developed perovskites as well, the thermochemical two-step water splitting cycle using perovskite oxides based on, lanthanum, strontium, magnetite. As you can see here, the oxygen production rate and hydrogen production rate, for different samples. And this green line shows the, the ratio. And here you can see, again, for different samples. So like that, we have been testing various redox materials and perovskite materials for, solar two-step water splitting cycles. And after, synthesizing the samples, for some reactor concepts, for example, this is another reactor concept. So in the previous slides, I presented the fluidized bed reactors, so which uses particles, as reacting material. But this kind of reactor uses this kind of, fixed bed, porous materials, porous ceramic structure as shown here. This would be coated by different materials. So for that, as you can see, zirconia foam matrix would be used, and this matrix would be, coated by different samples we have prepared. So finally, it would be like this. We prepare different samples, and after that, this porous ceramic structure would be, placed inside the reactor like a fixed bed. And then the solar radiation would be passed through the reactor, and then the thermochemical reaction, the so-called first step, the thermal reduction step, would be conducted for oxygen production, and subsequently the water decomposition step would be conducted for hydrogen production. So using this kind of ceramic porous devices, we have been producing hydrogen as well. Again, this is the reactor. So as I mentioned before, after creating the porous material, we place the porous material coated with reacting material over here, and we pass sunlight inside the reactor. It would be heated up. So as you can see in these figures, how these foam devices would be heated up by concentrated radiation. And when the foam device reaches more than 1300 degrees Celsius, as usual, we pass different gases like nitrogen and steam, and it would be reacted with the foam, and the hydrogen would be produced, and it would be passed through the outlet pipe, and we will cut it. So to understand this reactor, we need to know what is the temperature distribution, what is the gas velocity, and how the reacting gases would be going through the outlet pipe, how much hydrogen we can produce using different samples, and what is the size of the foam device. So all these parameters are important to optimize and finalize the design of the reactor. For that, we have been developing a numerical model, and as you can see, using our numerical model, we can obtain the detailed heat and mass transfer characteristics inside the reactor. So like that, we have been developing various thermochemical reactors to test various, redox and perovskites to produce syngas and hydrogen. Now, let me talk about the another part of the CSP plant, thermal energy storage system, which is one of the main components in CSP plant to produce electricity 24 hours. So as I explained, in the introduction slide, usually we supply cold heat transfer fluid to the receiver, where it circulates and receives the thermal energy, and it would be stored in the hot storage tank, right? And during the night time, we can take the hot heat transfer fluid to produce steam and electricity. So like that, we can produce 24 hours. I mean, electricity generation would be 24 hours around the clock. So thermal energy storage system mitigating the mismatch between the energy supply and demand. And this component is shifting the power generation period from peak hours of solar insolation to peak hours of power demand. As you know, during the noon hours, we have a very good solar insolation. The radiation would be very high, right? So during the noon hours, we can produce more electricity. But usually at what time we consume more electricity? Usually we consume during the morning hours or during the evening hours, right? So we can shift the energy generation period from noon hours to the peak hours using this thermal energy storage system, because we store the hot, heat transfer fluid in the tank, so we can take whenever we want. Moreover, during the cloudy period, during the rainy days, whenever we need electricity, we can use, the hot heat transfer fluid from the storage tank. So there are different storage concepts like direct storage system and indirect storage system. In direct storage system, the same heat transfer fluid would be used in the receiver and in the storage media, whereas the indirect storage system use different heat transfer fluids. The receiver heat transfer fluid would be different, the storage medium would be different. So we need additional heat exchanger. So let me explain the direct, or two-tank sensible heat storage system using this schematic figure for better understanding. As you can see, we have cold heat transfer fluid, right? So we supply the cold heat transfer fluid to the receiver, which is heated up by concentrated radiation. So the hot heat transfer fluid would be stored in the hot storage tank, Okay, so during the rainy hours or cloudy periods or at night times, we can take the hot heat transfer fluid for power generation, and then the cool heat transfer fluid would be supplied back to the tank. So in such a way, using the same heat transfer fluid, we can, supply from cold storage tank to receiver, and the receiver to the hot storage tank to the power block. So we don't need additional heat exchanger. So the efficiency would be higher than the indirect storage system. This is one of the example system, the Gamma Solar Power Plant using this kind of direct two tank sensible heat storage system. As you can see, these two tanks, are used for cold and hot heat transfer fluid storage. And this system gives 15 full load hour operation, which means if we don't have sunlight for 15 hours, we can produce 20 megawatt hour continuously for 15 hours. Okay, so most of the commercial power plants are using this kind of two tank systems, right? So to improve the efficiency and to reduce the storage tank size and the cost, to reduce the electricity cost, there are different approaches have been proposed from the past couple of decades. And our approach is to develop a single thermocline packed bed heat storage system as schematically shown here. So using this concept, we don't need two tanks. In one tank, we can do the charging and discharging process based on temperature stratification technique. So let me explain the concept using this figure. The hot heat transfer fluid collected from the solar field would be supplied to the thermal energy storage tank through the top part of the tank. So which exchanges the heat with the particles inside the tank. We may use sensible heat storage particle, or we may use latent heat storage capsules. We can use different samples. Let me come to that point later. So whatever the filling materials, so the hot heat transfer fluid exchanges the heat with the materials, and the cool heat transfer fluid would leave through the bottom part of the tank during the charging mode. And during the discharging mode, the cool heat transfer fluid would be supplied to the bottom part of the tank, which extracts the stored energy from the capsules and leaves through the top part of the tank. In such a way, using one tank, we can do the charging and discharging, processes. So by doing that, we can eliminate one tank and enable, potential cost reduction more than 35% compared to the two tank system. As a result, the electricity cost would be reduced significantly. So moreover, if we use latent heat storage materials instead of sensible heat storage material, it increases the energy storage density significantly. As a result, we can reduce the tank size smaller. So when we reduce the tank size, as usual, we can reduce the cost, because the size, when we decrease the size, the cost of construction will go down. So as a result, we can reduce cost as well. So to develop latent heat storage systems, we have been developing and using various phase change materials like sodium nitrate, sodium chloride, lithium chloride, and to develop thermochemical heat storage systems, we have been using different redox materials as well. Let me present. Can I continue?
உலகெங்கும் வாழக்கூடிய நெக்ஸ்ட் நேயர்கள் அனைவருக்கும் வணக்கம். நான் உங்கள் டாக்டர் வி ராஜ்குமார் சிவாச்சாரியார் பேசுகிறேன். வார ராசி பலன்கள் என்று சொல்லக்கூடிய வகையிலே நம்ம வார ராசி பலன் பார்த்துட்டு இருக்கோம். 25ஆம் தேதியிலிருந்து 31ஆம் தேதி வரை எப்படி இருக்கு அப்படிங்கறத நம்ம பார்க்க போறோம். வாழ்க்கையில ஒவ்வொரு வாரமும் புதிய கதை கொண்டு வரும் என்று சொல்லலாம். சில வாரங்கள் நம்மளை சோதிக்கும், சில வாரங்களை உயர்த்தும் அப்படின்னு கூட சொல்லலாம். அதே போல சில வாரங்கள் வந்து 12 ராசிகளுக்கான சவால்
Can you
சோதனை
hear me?
எல்லாம் கலந்த ஒரு ரோலர் கோஸ்டர் அப்படின்னு சொல்றோம் இல்லையா, அந்த மாதிரி தான் இருக்கும் அப்படின்னு சொல்லலாம். வேலை, தொழில், குடும்பம், காதல், திருமணம், விவாகரத்து, சொத்து, வழக்கு எது இருந்தாலும் இந்த வார கிரகநிலை உங்களுக்கு மறுபிறவி போல புதிய வாய்ப்பை தரக்கூடியதாக சில விஷயம் அமையும். ஒரு விஷயம் வந்து என்ன அப்படின்னு கேட்டா, ஒரு விஷயம் குலதெய்வ வழிபாடு தவறினால் நல்ல நேரம் கூட சற்று தாமதமாகிவிடும் அப்படின்னு சொல்லுவாங்க. அதே போல
Okay, thank you. Yeah. Okay, so in order to develop this kind of single thermocline packed bed heat storage systems, we need to develop PCM capsules, right? So as you can see, in order to develop PCM capsule, initially we prepare this kind of hemispheres, two hemispheres, and then we join them together, and then using electrolysis and nickel plating technique, we can create coating or plating around the capsule. And as you can see, to develop hemispheric pellets, so we usually use the automatic hydraulic press, and then we join them together like this. And after that, to perform or to test the thermal cycling, to see the performance and to see the degradation after number of cycles, we did thermal cycling tests as well. As you can see, the test would be conducted between 310 to 370 degree Celsius. And as you can see, after passing 1000 cycles, the stable, the capsule is stable and still working very well. So like that, we have been testing the degradation of the material for usually more than 2000 cycles. And to develop 1 kilowatt hour storage system, as you can see, it requires more than 770 capsules. As you can see, we usually prepare this kind of spherical capsules, and we fill the capsules inside the tank using this kind of perforated plates. And then, as schematically shown here, we join the thermal energy storage tank with the charging heater and the discharging heater to conduct charging and discharging experiments. And again, to analyze and to understand the performance of a latent heat storage technique, we developed a numerical model based on these assumptions, like PCM capsules behave as continuous medium, the flow is laminar and incompressible, the radiation heat transfer between capsules is negligible, rhombic packing, which means rough packing, is assumed in the cylindrical tank. The porosity along the radial direction has been defined by this expression. And in order to obtain the axial velocity along the radial direction, the extended Brinkman equation has been solved. And to obtain the heat transfer, the coupled heat transfer equations for heat transfer fluid and the PCM domains have been solved, as shown here. And these are the thermophysical properties of phase change materials used in the model. And to verify the model, we conducted charging and discharging experiments and simulations as well for the operating conditions shown here. For example, the initial bed temperature would be 286 degrees Celsius, and the fluid temperature and what is the flow rate you can see here. For these operating conditions, we did the charging experiments and similarly discharging experiments, and thermocouples installed at different locations inside the tank measured the temperature as a function of time. So for the same conditions, we did the simulation as well. As you can see, a good agreement has been found between the simulation and experimental results. So in such a way, we validated our model, and then using this model, we designed 50 kilowatt hour storage tank. And for the typical case, you can see the temperature distribution during the discharge mode and what is the heat transfer fluid temperature at different instants. and what is the PCM temperature. And you can see the phase change region, and like that, we can obtain detailed heat transfer characteristics inside the tank during the charging and discharging modes. Moreover, we can do the parametric analysis as well, like what is the influence of capsule size. For example, if we change the capsule size, how it affects the thermal performance and efficiency of the storage tank. And if we change the heat transfer fluid temperature, what would be the effect on the efficiency? And if we change the tank length or diameter or the ratio of these two, what would be the effect on the performance? So similarly, other operating conditions we can check, and we can optimize, and we can enhance the efficiency of the thermal energy storage systems. Like that, we can perform various things using the numerical model. And to increase the efficiency, we have been developing ceramic capsules as well. As you can see in the previous project, so we used metal capsules. We had some structural stability issues, and we have some issues due to corrosive behavior of or the metal parts due to the molten salt material, which is very corrosive. And to avoid the corrosiveness, and at the same time to increase the efficiency and performance, we used a silicon carbide a capsule. So as you can see, we prepared two hemispherical cells, and then we joined together to make a capsule like this. And then to test the heat storage performance, so we placed this capsule inside the heating chamber, and we passed heat transfer fluid from the top part of the tank, like a typical packed bed, the operating procedure. And we tested the heat storage performance. As you can see, to monitor experiments, different thermocouples were installed at different locations, and we conducted experiments for different operating conditions. And then again, to see the heat transfer behavior inside the capsule, we developed another numerical model based on these assumptions, like the solid and liquid phases of the passage material are homogeneous and isotropic. The flow is laminar and incompressible. The enthalpy porosity technique has been employed to predict the melting front. And based on these assumptions, these are the governing equations we formulated and solved by finite volume method. And again, to verify the model, we installed different thermocouples, at the center of the capsule, and close to the wall and close to the inlet. And initially, the whole capsule was maintained around 566 Kelvin, and then the gas temperature increased gradually from 560 to 610. And here you can see the gas temperature increase as a function of time. And this profile shows the temperature of the capsule at the center. So numerically predicted and experimentally measured temperature at different locations have been compared in this figure. As you can see, a reasonable agreement has been found. So using this validated model, parametric analysis was conducted, to check the effect of capsule size, to check the effect of Reynolds number, Stiffer number, and Grashof number. These are all important parameters to optimize and to obtain the generalized correlation of Nusselt number. We should conduct this kind of parametric analysis, and we did that. And this slide shows the thermofluid flow distribution of the capsule and the heating chamber for a typical case. And as you can see, the left side of the heat transfer fluid domain shows the temperature distribution, and the black and white temperature, the black and white gradient color represents the melting behavior and the melt fraction. And the right-hand side of the heat transfer fluid, this streamline represents the velocity of the gas. And this velocity vector represents the velocity distribution of the molten phase change material flow inside the capsule. And as you can see, initially there was airspace for thermal expansion, and as it melts, it shrinks. So the airspace is gradually decreasing, you can notice. And moreover, during the melting process, since this solid phase is, sinking inside and pushes the thin liquid layer formed at the inner surface of the capsule. So as a result, it pushes the liquid, towards the top part along the inner surface of the capsule. As a result, it creates a kind of anti-clockwise natural convection pattern, which increases the heat transfer rate. So like that, we can obtain very detailed heat and mass transfer characteristics inside the capsule. And in this slide, you can see, if we increase the gas flow rate, by fixing other operating conditions constant, like capsule size, initial temperature, and fluid temperature, all constant, and only variation is the inlet gas flow rate from 30 liters to 70 meter cube per hours. As you can see, when we increase the gas flow rate, the velocity obviously is increasing. And here you can notice that the melting rate is faster because the heat transfer rate is faster as well. And in this graph, you can see the melt fraction as a function of time, the black line profiles. And the heat flux at the outer surface of the capsule has been predicted as well. So as you can see, during the initial stage, as the temperature difference between the outer surface of the capsule and the center of the capsule is very high, the heat flux is very high. So as soon as the melting process starts, so the heat flux profile, it's like, as you can see in this profile, almost like flat. So like that, you can see the melting behavior accordingly, what is the heat flux at the outer surface of the capsule. So it is very obvious that when we increase the gas flow rate, the heat transfer rate is increasing. As a result, the complete melting time is decreasing. And when we increase the flow rate around 57%, the complete melting time, decreased around 35%. So similarly, we conducted simulations for different, Stephen numbers, which means what is the effect of, gas temperature. If we change the gas temperature, how it influences the overall performance and, the complete melting time. As you can see, after 10 minutes of heating, you can see that here the heat transfer rate is very high for high Stephen number case, because the inlet gas temperature is very high. As a result, the melting is very faster and it reaches very quickly. So around 900 seconds, which means 15 minutes. Whereas for 519 Kelvin inlet gas temperature, it took around 3,000 seconds. So again, the profiles and the explanations are same. And here you can notice that when we increase the Stephen number around 68%, the complete melting time is decreasing around 66%. And then we did the dimensionless analysis to obtain the generalized correlation for melt fraction and the Nusselt number. And using this Nusselt number, we can calculate the heat transfer rate between the capsule and heat transfer fluid for thermal energy storage system. And this is another project. In this project, we developed a metal capsule, but to avoid the corrosive issues, we this kind of ceramic coating we have made inside the capsule, inner surface of the capsule. So for that, we used a plasma spraying technique. So this is the plasma torch. It usually produces high temperature jet like this. So if we inject ceramic particles inside the high temperature jet, it would be melted, and the molten particles would be splashed over the substrate to create coating. So we did alumina coating over the SUS substrate, as you can see. And the encapsulation technique is almost same. So we prepared two hemispherical capsules, and then we joined them together, and then we welded at the in the joint to make this kind of spherical type of capsule. And then here in this table you can see what is the alumina coating thickness and details, and the other concept is same. So we tested this capsule for latent heat storage tank using sodium nitrate as phase change material. And then we did the thermal cycling tests. As you can see, we did more than 50 cycles. And as you can see, the initial and operating conditions of the cycling tests, you can see in this graph. And as you can see, when the temperature increases and reaches the melting temperature, and it's almost constant. So as soon as the PCM material melted, the temperature profile increases suddenly. And after this point, the discharging experiment conducted. As you can see, when it reaches the melting temperature range, it's almost like flat. And as soon as the material is solidified, the temperature response is very quick. So like that, we did charging and discharging experiments of plasma spray coated samples as well. And these capsules also promising, and we have been testing them. So to develop this kind of capsules, we have been using various materials as well. For example, we used iron germanium alloy as phase change material to develop PCM capsule, and it has potential. It has potential as latent heat storage material. It gives higher storage capacity than other salt-based PCMs, and it gives quick thermal response as the thermal conductivity of this material is very high, and this material is thermodynamically stable, metallographic structure, and non-reactivity with the shells. That is one of the important issues when you consider salts as phase change materials. And to prepare these materials, the iron germanium alloys would be synthesized by melting iron and germanium powder in a vacuum condition and heated at 1400 degrees Celsius for 2 hours in vacuum to melt the powder and form ingots of iron and germanium alloy. These ingots would be cut into pellets, and then these are all usual procedure. We take XRD to check the XRD patterns, and we usually do this kind of time derivative dt by dt profiles to check where the melting starts and where the melting ends, and what is the latent heat of fusion, and all these details we obtained from these profiles. And here you can see we tested different samples like iron germanium 75. It means 75 weight percentage of germanium, 25 weight percentage of iron. So like that you can see. So this sample means 10% of iron and 90% of germanium. So like that we tested various samples, And yeah, here you can see the accumulated storage capacity of iron germanium alloy is much higher than other salt materials like sodium chloride, lithium chloride. So as you can see, these materials gives, a very good accumulated storage capacity, per unit volume. So in this graph, you can see the accumulated storage capacity, per unit weight. But this is very important to compare different materials because the unit volume is important. Similarly, like iron germanium alloy, we developed copper germanium alloy as well. And yeah, we did the XRD to test, the XRD patterns and different amount of doping or percentage, and what is the heat storage capacity. As you can see, this material also very nice to increase the heat storage capacities. So based on the packed bed setup, we developed different passage. I mean, we developed different phase change materials, and based on the same packed bed approach, we have been testing and using different sensible heat storage materials as well. As you can see, we use alumina balls, instead of PCM capsules, and we tested different rocks, river rocks as well, as you can see, as a heat storage material. So using this technique, we can increase the energy storage density. At the same time, as these materials are very cheap, we can develop inexpensive heat storage systems as well. So that is the main advantage of developing this kind of sensible heat storage system. So this is the prototype we developed in our research center. As you can see, we filled alumina balls, and then we did some experiments and the simulations for the operating conditions as shown in this table. And we compared the experiments and simulation results. As you can see, we see a good agreement. Like that, we verified our model, and then we tested different, natural river rocks as sensible heat storage material. These are all the rocks collected from Morocco. So through a collaboration research with CIC Energy Gune Research Center in Spain, through this international joint research, we tested these river rocks as heat storage material. And based on this material, we designed a tank, in pilot scale, around 25 megawatt hour storage tank, and other specifications you can see here. What would be the pellet diameter, and what is the operating conditions and range of operating conditions. So all specifications you can see in this table. And using the developed model, we studied the thermal performance during the charging mode and discharging mode, and what is the heat storage capacity. In solid phase, how much heat can be stored, and in heat transfer fluid, in this case oil, in oil, how much heat can be stored, and what is the total heat storage capacity of the tank. So this kind of details you can see in this graph. So like that, so we have been testing various materials, and then we have been developing small lab scale prototypes to test how these materials or prototype tanks work. And based on these results, we expand the design and tanks to pilot and commercial scale. This is our usual procedure. So in this slide, you can see what are the materials we have been focusing on to develop different types of thermal energy storage system prototypes. To develop latent heat storage system, what are the materials we are mainly using, and what are the sensible heat storage materials? And to produce hydrogen and syngas, we mainly use cerium oxide, and we have been developing some perovskites as well. So this slide gives an overall summary of our major research activities in recent years. And yeah, this slide, gives you an overall, a view of different types of thermal energy storage systems. When we go from sensible to thermochemical heat storage systems, the complexity would be increasing. At the same time, the heat storage capacity of the thermochemical heat storage system is very high compared to sensible heat storage system. Okay, thank you for your kind attention. Yeah.
Participants, if you have any queries, you can ask now. Participants, if possible, you can post your questions in chat box also.
Sir?
Yeah.
Good afternoon, sir. Really, it is a nice and wonderful and informative talk, sir.
Yeah, thank you.
Yeah, I want to ask something about the choice of material like cerium oxide. Instead of cerium oxide, any other metal oxide you have tried, or it is possible to use as a thermal storage for hydrogen production process?
Yeah, actually, there are different materials, and the reactor concept would be different. For example, volatile material also you can use, like zinc oxide. So in that case, when you pass the materials inside the reactor, so after the reactor, as the material is volatile, it disappears, right? So that is one of the materials tested by, PSI, Research Institute in Switzerland, and ferrite. The ferrite material can also be used for two-step water splitting cycles. So apart from ceria, there are some other materials. Yeah, if you look at literature, you can see many other materials. But among these materials, cerium oxide is very promising. The efficiency of cerium oxide is very nice compared to other materials. That's why we are using that.
And one more question. So, what is the purpose of sending nitrogen gas into the reactor?
Yeah, let me. So this one, right?
Yeah.
Yeah, the first step. Yeah, so can you see here? So this is the first step. The cerium oxide would be reduced into lower valence metal oxide, and it produces oxygen, right? So the nitrogen gas won't react with oxygen. So we are using, so any, unreacting gas we can use. So we are using nitrogen.
It is possible to use some other inert gas like argon or
Yeah.
helium like that?
So this is just to, fluidize the particle, right? This gas is to, fluidize. If we pass the gas, then only the particle will fluidize inside. Otherwise, it won't fluidize. So the heat transfer rate would be very low. So any inert gas is okay to perform thermal reduction step.
Thank you, sir. Thank you.
Yeah. Thank you. Yeah, I got another question from Glita Sumangali, Dr. Glita Sumangali. Will this be applicable during rainy season? Yeah, I guess you're asking question based on this concept. So yeah, it's possible, for example, during the morning hours, if you have sunlight, so I guess you understood this concept. During the morning hours, if you have sunlight, the sunlight would be converted into thermal energy, and then the thermal energy would be stored inside the tank. Okay, so we have enough amount of hot heat transfer fluid. During the afternoon, if there is a rain, so obviously there won't be sun, so we cannot get hot heat transfer fluid from the receiver. So in that case, we can take hot heat transfer fluid from the stored tank to generate steam, and we can generate electricity. So it is possible during the rainy days. But if the rainy day is continuous for a couple of days, in that case, if we don't have enough hot heat transfer fluid, we cannot produce electricity. So it depends on what is the storage capacity of the storage tank. Some storage tank gives 15 hours capacity, which means for 15 hours without sunlight, we can produce electricity. For example, this Gamma solar plant. So here you can see the storage capacity is 15 hours, which means for 15 hours, if there is continuous rain, this plant can produce electricity 15 hours. So after that, it cannot. I hope you understood the concept.
So participants, if there are any
Yeah.
queries, you can ask now. So I think there are no more questions.
Okay.
So on behalf of the management, principal, faculty, and participants, I take this opportunity to extend a heartfelt gratitude to our distinguished resource person, Dr. Selvan Bellan, for your valuable time, insightful presentation, and enriching session today. Your deep knowledge and clear explanation have truly broadened our understanding and inspired us to enhance our teaching and research practices. We sincerely appreciate your efforts, sir. Thank you once again for making this session so meaningful and impactful. Thank you so much, sir.
Thank you. Yeah.
Thank you, sir.
Yeah. Thank you.
So participants, the feedback link is given in the chat box. You can fill it now. So within a few minutes, the next person will join.
Okay. See you guys. Thank you.
Thank you, sir.
Yeah.
Participants, we have 2 more sessions today. So after completing your feedback, please wait for a few minutes. The next person, the resource person, will join shortly. So we can move to the next session. So on behalf of Mathanam College of Engineering and Technology, it is indeed a privilege and pleasure to welcome you all for the next session of this faculty development program. We're delighted to extend our warm greetings to our respected management, principal, heads of departments, faculty members, and all dedicated participants who have joined us today. So it gives me immense pleasure to extend a warm welcome to our distinguished resource person, Dr. Jayakumar, Principal Scientist, CSAR Sikri, who has kindly accepted our invitation to share valuable insights with us today. We are truly honored by your presence and look forward to an enlightening session. At this juncture, it is my privilege to invite Mrs. Jacqueline Shobha, Assistant Professor, Department of Electrical and Electronics Engineering, to formally introduce today's eminent resource person to the gathering. Ma'am?
Yes, ma'am.
Yes, ma'am, you can take over.
Thank you, ma'am. Good evening to you all. It is my privilege to introduce our guest, Dr. Mani Jayakumar, Senior Scientist at the Central Electrochemical Research Institute, Karaikudi. He holds an MSc, MPhil, and PhD and is a distinguished researcher in the electroplating and 61 citations and significant contributions to fundamental and applied electrochemistry. Dr. J. Kumar's expertise span electrodeposition and electroplating of refractory and noble metal alloys, molten salt, electrowinning of critical and rare earth metals, recovery of critical metals from secondary sources, and the development of novel anode and electrolyte system for next. His pioneering work in the areas of energy storage, rare earth recovery, and advanced electrochemical processes has placed him at the forefront of materials and energy research. Beyond his research, he actively collaborates with national and international scientists, significantly enriching the field of electrochemistry. We are truly honored to have such an eminent scientist with us today, and I warmly welcome Dr. Mani Jayakumar to address this gathering. Welcome you, sir.
Thank you, ma'am, for introducing resource person to the gathering. Now, I hand over the session to our esteemed resource person, Dr. Jayakumar. Welcome you, sir.
Yeah. Good afternoon, ma'am. I think.
Good afternoon, sir.
Okay. So this is going to be the last before session, right?
Yes, sir. Yes, sir. So next we have another one session.
Okay. Is the screen visible? Is the slide
Yes, sir.
moving?
Yes, sir. The screen is visible.
Okay. Just before I start, what is the background of our faculty, ma'am? They're from engineering college or from arts and science college also?
Both the colleges. So it is like a faculty development program. So the faculty from different organizations will be attending this session.
Okay. They will be from chemistry background, physics, all
No,
background, right?
both physics, chemistry, and also engineering also, sir. The research scholars
Okay.
also participate.
Okay. There are nearly 77. Okay. So hope the slide is visible, right? So next, maybe 1 hour or so, what I will try to give is whatever we are working in the field of electroplating. Okay. Some of you who are from the chemistry background may be aware that electrochemistry is part of your physical chemistry, and we know what is Faraday's law, its application, and batteries. And last 10 years, there is a lot of interesting work in batteries. So some of you may be working in batteries, some of you at least may be aware batteries is one field. So in the field of electrochemistry, one unique area is electroplating. Okay, so we will just maybe I will not go too much into deep and give a lot of unwanted keywords or jargon to confuse you. My aim is just to give an idea what we are doing at CSR Secretary in the field of electroplating. Okay, although we are doing electroplating or we are using electroplated equipments every day, We just don't know what is the importance of electroplating, because we know battery because we have batteries at home for the UPS, maybe in our mobile phone, laptop, or maybe in some different places, even in two-wheeler, four-wheeler, we use battery. We have some idea about batteries. In the entire field of electrochemistry, batteries is something which is well known because it is related to energy storage and we use it every day. Although we use a lot of electroplated equipments also every day, it can start from imitation jewelry. Just we don't know that it is basically a everyday business as well as for some niche special applications in defense and aerospace also we are using this kind of electroplated samples. So we will just try to give you a flavor of what Sikri is doing in this field, what is the background of it. Before I start, this is my outline of the talk. Before I directly go into the field of your electroplating, just I wanted to give a small overview about why we do electroplating. The main idea of electroplating is corrosion, because the basic life, whatever for an equipment, for a coating, for any sample, or even our everyday equipment like a steel cupboard, maybe two-wheeler, four-wheeler, everything depends upon how well it is able to prevent itself from corrosion, or how you can make sure that corrosion doesn't happen in a significant maybe 10 years, 20 years, what we call it service life. So to overcome corrosion only, we are trying to do electroplating. Okay, maybe you may be surprised to know the total corrosion of material, whatever globally, it is $2.5 trillion. So 1 trillion is 1 lakh rupees. So $1 trillion, $1 lakh. So 2.5 lakh dollar is the total amount of material we lose in corrosion. Why we get corroded? Because we don't use gold and silver for making equipment and everyday items, right? Whether it is our TV, washing machine, iron, they are made up of plastic or is metal. Metal is predominantly mild steel because that is cheaper. We cannot use stainless steel everywhere. None of our two-wheeler, four-wheeler, nothing is made up of stainless steel. It is made up of mild steel and it is electroplated. So the loss which every day, every year, on an average we lose is $2.5 trillion. Okay, that would be a data for you. So when we go back to the field of electrochemistry, just let us have a quick idea about what is CSR Sikri. Maybe my other speakers from Sikri, Dr. Pandikumar or Dr. Tamilisan, maybe somebody must have covered. So just I wanted to spend a couple of minutes here. So CSR Sikri is part of CSR group of laboratories. Abbreviation is Council of Industrial and Scientific Research. This is spread across 38 places in the country. In that, three labs are in Tamil Nadu. So Sikri is here. Uh, So Sikri is here. So we are in the tri-junction of Rameshwaram, Madurai, and Trichy. So we are in the middle of this triangle. So we are around 2 hours from all these places. Another two labs are located in CLRA, which works on leather, and structural engineering, which is also working in structural in SERC, Structural Engineering Research Center. So these three labs are in Sikri. The primary reason why such a place got because all our labs, if you see, there in Delhi, Bombay, Chennai, whereas Sikri is in a very remote place even today. Okay, so although Karipudi is become a corporation, but it is still a small center. So this particular town, that is also the hometown of Dr. Alappa Chettiar, who is the founder, brain behind this um, uh, CSR Sigris at say, Karakudi, because he is also happened to be a friend of. You can see the photos here. Pandit Jawaharlal Nehru is there, and this is Swan Susarum Bhatnagar. He is one of the founders of CSR. This Dr. Alappa Chettiar, and the foundation stone was laid by Pandit Jawaharlal Nehru in 1948, and our institute is as on date close to 78 years. So you can see the foundation stone as well as the inauguration by Dr. Sarvapalli Radhakrishnan. So this gentleman gave 300 acres and 50 lakh rupees in 1948 because he was a very big industrialist. And from 1953, in the last 73 years, our equipment, CSR Sigri is working in different areas of electrochemistry. So just to give you a different, whatever area we work is, we are working on corrosion protection. See, corrosion assessment is corrosion division's role, or polymer coating. Corrosion protection by mild steel is our division's role, electroplating division. and electrochemical power sources which work primarily on batteries. Electroplating and electrometallurgy division, which is my division, we work on plating, electroplating, metallurgy as well as coatings. And another three divisions, primarily electronics and electrocatalysis, primarily works on sensors and different kind of electrocatalysis which is related to energy, like hydrogen evolution and the production of carbon, conversion of carbon dioxide to fuel. Those is the target of this electronics division. Electrochemical processing primarily works on hydrogen production by different route. You may be knowing like today rare earth, batteries, hydrogen is also becoming very predominant word. So the primary idea of this particular division is to have a hydrogen electrolyzer technology. And the organic and materials electrochemistry division works on gamut of different things: organic, electro-organic, and material chemistry, which is primarily focused on um, like supercapacitors and to some extent solar cells and the conversion of different organic materials by electrochemistry. And we also have two extension centers. One is in Mandapam, primarily for the corrosion, and for the people who are maybe new, the Tiruvallur statue in Kanyakumari, the Pamban Bridge, and the railway bridge in Rameshwaram. All are maintained by CSR Sikri, and it is not like we maintain. We regularly provide consultancy so that what is the state of the corrosion in seawater, how the seawater corrosion is affecting different structures, whether it is a statue, whether it is a railway, etc. And Chennai unit is primarily energy center. So when we say energy, anything related to battery, fuel cell, all the research premier of our this one works at the Chennai Extension Center, which is close to the tidal park. So this is a typical CSR secret lithium ion pilot plant, wherein if you come with a powder, which is a cathode material, it is possible to make a lithium ion battery. Indian owned lithium ion battery. All that we need is we have also developed different cathode material, which is also patented. You can see the details here. And we have an assembly line where assembly means if we give a powder, we will make it into a coating. That coating will be made into a battery, and we can fill the electrolyte and make it work like a battery. So the capacity is around 1,000 cells per day. So this is a flagship of CSR Sikri as well as in the entire CSR system. And this is a Sikri, where Sikri campus, Karagudi campus, we have developed the super capacitor. One of my colleague, Dr. Satish, has developed, wherein we have developed the carbon which can be used for super capacitor application. So you can see the details of whatever the super capacitor carbon grade, and this technology has been transferred to a private company, and they started the production already. And as I mentioned, this electrolyzer primarily in hydrogen evolution because what happens is one of the primary idea of this electrolyzer is we don't want to have the impact of your crude oil, petrol, diesel. So that is going to be the existing process for driving a locomotive or a diesel based all systems, whether it is the container ships, passenger ships, and the trains, flight, everything is based on the fossil fuel. Now, once green hydrogen becomes a reality, it is possible to think equipments just by pouring water will be split into hydrogen and oxygen. That hydrogen can be used as a fuel. So the aim of Sikri is to develop this kind of electrolyzer. When I say TRL, that is the level where is the technology. Anything beyond 5 is considered that industry will be able to take. Now, Sikri has developed this kind of different electrolyzer, PEM electrolyzer, alpine electrolyzer, as well as different solar-based electrolyzer. The aim is to develop a technology and transfer to a company, maybe like ONGC, BHEL, or a different ATPC, different companies. They will market, they will manufacture it and market it. So our job is to develop the technology. And these are some of the labs, national institutes, private companies, strategic agencies. You name a company, it will be there. BHEL, ONGC, or maybe DRDO, VSSC, or different lab, NALCO, Hindalco. Maybe, before I just go, So the field of electrochemistry, unlike other fields, it is not a very old field. I think slides are moving, right?
Yes, sir.
Yeah, okay. So if I take the field of battery, everybody knows lithium-ion battery, but lithium-ion battery is today's technology. If you take 220 years back exactly, there was no battery at all. Michael Faraday invented some. There's a relation between magnetism and electricity, and electricity didn't even come as a reality. So it was in 1800. Alexander Volta, who is native of Italian, he developed this voltaic pipe. All that he did was he made steps, a packet of zinc and copper. In between, there's a cloth which is having a sodium chloride or maybe any other salt as a separator. So technically, this is the same. The battery didn't change till now. We have one cathode, we have one anode, and all of you who has done MSc chemistry must be able to know which will easily lose electron, which will gain the electron. The one which is already easy to release the electron, it is non-noble, and the one which wants to take the electron, it is going to be noble. The same applies for your zinc and copper. So typically, when we take these two metals, because one is at positive potential 0.34, another one is at 0.7. So technically, you have around 1 volt. So when you have these two metals separated by a cloth, which is having some salt water. Salt water is nothing but your electrolyte. You can develop a voltage. So he found out it is possible to stack them and increase the voltage. So that is the primary idea of whatever he did. So this particular very idea, voltaic pipe, when we say pipe, it is the cathode and anode are piled in sequence. So one after another. So in such a way you can produce some amount of voltage. This is one of the earliest study because whether lightning arrestor, which is Benjamin Franklin or Michael Faraday, they all invented 20 years before Volta that something is there, some electric field is there, and electric field and magnetism is related. But they don't know from where to produce electric field. So we cannot wait whenever there is lightning thunder to produce voltage, and that will be in thousands of volt. So Volta made a practical solution. I will make a simple energy generation device or maybe a battery today. So this will provide continuously some amount of current as long as your separator is having some electrolyte as well as your cathode and anode are intact. They don't dissolve. Okay, this is the basic idea of your Volta. Maybe in the same time, what happened was this is considered as a father of Italian chemist who is Luigi Brugnelli. He is considered as a father of electroplating. But he is although an Italian guy, but he didn't do the invention and stay in Italy. He went to France. That is where this electroplating field itself was invented. So when I say electroplating, plating is nothing but coating. So when I want to do a coating with current, if you want to apply current, there must be something which has to conduct the current. Example, some ions, some electrolyte, something. Pure water doesn't conduct electricity, you may be knowing. So similarly, it is not possible to do electroplating without current. That will be called as painting. So painting and electroplating are same. If you use organic polymer, that is called as painting. If you use electrochemistry and plate a metal or alloy, that is called as electroplating. So for till from 1805 when he invented, next 30-40 years, nobody knew that French had this kind of technology. Only after 40 years, the Russian as well as English people discovered it, which resulted into the field of electroplating. And also, it is not like electroplating was made for everybody. When they made the electroplating, they were very sure this is like a royal, rich people. Only the kings, monarch, aristocrat will be able to use because you don't need platinum, you don't need gold, but you can see the finish here. So by using copper or maybe steel substrate, you can coat with silver and it will give you a very silver finish. You don't need 100% silver into the spoon or fork. All that you have to do is just you have it in the some low grade some material, or that you can do the plating. So the main idea is we don't want to use full material. We wanted to coat only surface. That is the main idea of electroplating. Just like we don't construct a house with paint or coating, right? We construct a house with TMT bar, with concrete, finally, and with some lime. Finally, we do only finish with your painting. Here also you do only finishing. You don't do the bulk. So when I say electroplating, it is nothing but when I pass current, there is a movement of ions, and one ions get deposited as a coating. So typically, what you will have is you will have a anode and a cathode, and cathode is where my metal wants to deposit. So when I am thinking as a electroplating, maybe if you are given a small tank, you want to do electroplating means you will require one DC rectifier, which is source of energy, which is a source of you can use battery also. In fact, with 1.5 volt our normal everyday battery itself, there are a lot of YouTube videos on copper plating. Okay, because copper being noble metal and potential being positive. So when you apply the potential, nickel is relatively less noble, whereas copper is more noble. So nickel gets oxidized, and over copper nickel gets deposited. So the reaction, if I have to take maybe in layman term, this is what is in the reaction. So one side you have positive electrode which loses electron. When it loses the electron, that is called as oxidation. On the other side, we have the opposite electrode, which is cathode, which gains the electron. So that is called as reduction. So oil is oxidation is loss, reduction is gain. Maybe if you want, you can abbreviate. So you can easily remember that oxidation is nothing but loss of electron, and reduction is gain of electron. Electroplating is gain of electron. So now if you pass current with two electrode, whether my electroplating will happen, I have one battery source, I have two electrode. Whether my electroplating will happen, can anybody answer? Anybody? Hello?
Yes, sir.
Yeah, can anybody answer the question? Just if I have a battery and two electrode, whether electroplating will happen?
So we need electrolyte.
Yeah, exactly. Oh, thank you. So you need the electrolyte, which is going to be the where your metal ion will be there. So when we do electroplating, the positive electrode can be stable electrode or soluble electrode. If you want to do nickel plating, I use nickel as the anode. Or in some cases, in case of gold tunnel, we don't remember uh, take the anode as the particular metal. We use it as salt also. The salt will be dissolved in a suitable solvent, mostly water, and that becomes the electrolyte. So electrolyte is where your actual reaction will occur, and so you can take the typical case of nickel here. So nickel get oxidized at the anode and comes to the electrolyte, and nickel 2 plus goes travels into the electrolyte. It is not like the nickel which is coming from this end of the from this anode, it will travel all the way to the cathode. No, in reality nothing happens like that. Nickel dissolves little bit from the anode and become ionized, whereas whatever nickel in the bath, part of it gets oxidized, I mean reduced, and that nickel gets deposited onto the cathode. So the basic idea is whenever we have a electroplating, the metal ion dissolves at the anode in most cases, whether it is nickel, zinc, copper, so many systems, and most of the non-noble metals. In noble metals, we cannot do like that. Okay, noble metals require a not soluble anode, insoluble anode. Okay, so in this case, if I have only the nickel salt in the my electrolyte, that will be insufficient to have called as electrolyte. Whenever we have a cathode, there must be catholyte. We also must have an anolyte, or maybe cation or anion. Simple to say. When we have only both, one of the species will go to the cathode, another will travel to the anode, so that the reaction equilibrium is maintained. One side is reduction, another side is oxidation. So whether it is nickel sulfate, nickel chloride, so nickel will travel towards the cathode and sulfate will travel towards the anode, and they will either gain the electron or lose the electron. Okay, so that is the basic idea of electroplating. So when we say electroplating, it is possible that you can have different systems. I can deposit a metal, I can deposit a alloy, all will come under electroplating. No, I do not gone for a metal reduction. I want to oxidize the metal. That is whatever you black utensils we use in our home, like pressure cooker, which is made up of anodized. Even there are jewelries today available, different items which use available. People call it as anodized jewelry. It looks black, but once it is black, there won't be any scratch. They are very good and have very long service life. In addition to electroplating, there is something called a specialized micro coating which is used by pulse plating, where instead of giving directly DC current, because you cannot do electroplating by AC current, that is very limited area where AC current is used. Whereas if you use pulse plating, we on the current for some time, we on it for half time. There is a time, for example, if there is 1 minute, theoretical I am telling, for 10 seconds power is on, 5 seconds off. 10 seconds it's on, it's off. So when compared to continuously giving some current, say 1 ampere if I am giving, instead of giving that current for a very long time, if you have a pulse technique, on, off, and there are additional technique called as reversible pulse technique, where you on for some time, metal gets plated and you dissolve that part of the surface. So more better sticking. Sticking is in our electrometallurgy, electroplating term, it is called as adhesion. Sticking is done very easily. So pulse plating is an advanced technique which is used in some developing special coatings and something called as electrolysis deposition. When they say electrolysis, electron is involved. Only thing you don't give electron from outside because you have a rectifier. Rectifier is source of power. I am having the rectifier passing the current, and the reaction is occurring at the cathode and anode. And if I am not even having the rectifier, if one of the metal ion, say if I am taking a copper sulfate solution, and if I am dissolving either maybe our zinc or if I am taking any mild steel, as you all know, you might have seen some videos also, easily copper will reduce by gaining the electron from zinc or from mild steel. So how much fast oxidation happens at the mild steel? Same speed this copper will also deposit at the cathode. This is called as electrolysis deposition. You don't need rectifier, you don't need electrode. You need only a substrate. In substrate, one part of it small amount will dissolve. Because of that, surface becomes very hard, rough, which leads to the subsequent deposition. Because when something is dissolving, it has to release the electron. When that is releasing the electron, it will release to the nearest noble metal which is available. For example, in this case, copper. So copper will reduce and that will deposit. That is called as electrolysis deposition. So some of you may be doing calculation with this. Some of you may be already knowing what is Faraday's law. Okay, so when I say Faraday's law, primarily it is kind of a law which governs all the electrochemical equations, whether it is battery, whether it is your supercapacitor, electroplating, hydrogen, everything comes under Faraday's law. And Michael Faraday, who is considered as a father of electrochemistry, he was the one who gave this kind of Faraday's law for the first time. Simply, he developed two laws. First is a very simple law. I give a current, something is reactive, whether oxidation or reduction. How much current I give, it is proportional to how much it is formed. Simple. Now, whether if you pass current with all the metals or systems, all the salts, whether all of that will give current, I mean, product in the same level depending upon the current. For example, I am applying 1 ampere, 1 ampere for some 1 hour. In whether both two electrodes, say one is made up of platinum or gold for that matter, the other one is made up of mild steel. Whether both of these systems will give the same yield? No. They will give additionally one more aspect called as electrochemical equivalence circuit. Equivalence. When electrochemical equivalence is depending upon the molecular weight, depending upon how much electron is transferred. Because for silver it is 1 plus, 1 plus to 0. Silver Ag plus to Ag 0. In case of copper it is 2 plus if it is going to be cupric, and if it is gold it can be 3 plus also. So when it is 3 plus, it is gold 3 plus, its atomic weight divided by, you can see the calculation here, it's a molar mass. Molar mass of your gold, how much current you pass, how much current density you pass. When I say current density, it is nothing but how much current was given in the particular area. Okay, for example, if I am giving 1 ampere per centimeter square, or if I am giving 1 ampere per meter square, so the one which is having centimeter square will have higher current. That is the basic logic. Okay. When we pass same amount of current, depending upon the molecular weight of the particular target metal, depending upon how much electron transferred, like I told you, nickel 2 plus, silver 1 plus, and your gold 3 plus, depending upon that number of electrons transferred, and you have a Faraday's constant, which is nothing but multiplication of charge of one mole of electron, charge carried by 1 mole of electron. The value is approximately around 96,000 coulomb per mole. Okay. So now, given all these parameters, Faraday simply gave two laws. If you pass on, something will form. How much it is forming, it is related to the current pass. Second, if you're passing current between two systems, both will give different amount of product depending upon their molecular weight and number of electrons. This is the Faraday's law. This is the pulse plating and pulse reverse I was telling. Pulse reverse is a unique technique. Instead of continuously giving current, you have on time, off time. So current runs for some time, say 10 seconds. I am telling these 10 seconds, 1 minute only for your understanding. Actually, it will be in microseconds. So we will have some cycle, this kind of on off cycle, technically 30 to 60 in a second. So technically it will be on in microseconds, maybe few 1 or 2 microseconds per cycle. So by passing current and switching off for some time, it is possible to have a very uniform coating, which is better than the pure direct DC current. Now people thought, okay, I will make it on off. It's still working. It is like when we go for a long run, we stop in between to have some small amount of water and to refresh ourselves. That is what is happening in the pulse. This is where electron deposit. This is where the metal is depositing. How much current you are supposed to give, you give it. And this is where no metal will deposit. And this is the after. Okay. Now people thought, okay, if we make it on and off only, this is sufficient, or I have to do something different. So people, we come with so many crazy ideas, right? So people thought, okay, I will switch it on for some time and let it run. After that, I will stop it, then I will go back to the opposite side. So from the cathode itself, small amount of metal will dissolve. That is called as the typical pulse reversal current. So when it is dissolving, makes some roughness on the surface. The roughness is what causes to next cycle. For example, I deposit some metal. I deposit here. Then I go here, I apply just opposite current. So when I'm applying opposite current, technically what happens is my particular metal ion which got deposited will again become an ion. So when this is happening in very, very short time, immediately metal will get activated. It is possible to get a much better uniform deposit, which people are using today for hydrogen and so many other applications. This is a very interesting idea. Just some gentleman thought, okay, I have a small current source, what we call as rectifier. Rectifier is nothing but our AC current converted to DC is called as rectifier. Now there is a equipment which gives us current. But why I have to keep on electrolyte in some tank and create so much issue? Is there possible something to mix our traditional painting? Maybe I'm just wondering, traditional painting along with your typical electroplating. Then he thought, okay, why don't we come with the idea of what we call as electroplating, which is done by brush plate. Brush is nothing but the brush which is already here. So the aim of this brush is to give a uniform coating which results in very intricate area. For example, I made a factory. In that I used some electroplated component. If that full equipment I cannot cut and remove means, for example, like Kalpakam or maybe some shipyard, some big equipment, we cannot take it to lab and do any analysis. So it will be in that shape only, in that place only. By brush plating, all the techniques are same. It is easy to deposit inside area also. That will make you the interpreting very interesting, because otherwise you have to take the cathode and anode immerse into the electrolyte. And when people thought maybe 20 years, 30 years back, this electrolyte is primarily to just deposit and get a uniform deposition. But brush plating is like a normal plating with current. Simply you have to understand. I'll just show you a small video that will give you a more clear picture about. Yeah. You may not wonder, okay, is the slide visible? I mean, the video is visible? Can somebody confirm? Hello? Can somebody see the video? Hello? Okay, okay, yeah. Thanks for the message, Dr. Rajesh. So, just to next 5 minutes, you can give an idea what is brush plating. So, maybe coming back to the class, can somebody maybe tell in your comments? Just I want to know uh, what is the color of your typical gold plating? Whatever you observe from the video. Anybody there? Okay, yeah. So gold is deposited on this different logos, right? So whatever we see the logo every day, Toyota, Mercedes, Benz. So this is a typical application of your interpreting process for a everyday object. It is not like I am saying everybody is using Benz every day. The same technique can be used for jewelry, what we call as imitation jewelry. We can make it with copper and gold can be deposited. Can somebody tell gold was in which electrode? What was the color of the wire which was connecting to the gold? I mean, the white color thing, which is like a brush, which is moving and making the gold color coating. What was the color of it? There were two terminals, I think, if everybody will agree. In which terminal this gold was getting coated, or where they added the electrolyte first? Yeah, right. Okay. So gold will be at the cathode. And can somebody remember what was the color of the lead in that particular video? You have different color: green, violet, blue. No, I am talking the color which is connected with the rectifier. There is a coiled wire which is coming from the rectifier where gold is depositing. I mean, from where that gold electrode is connected. Maybe we will just see the color here. See? So red is the code for your cathode, and you can see in all your electrochemical cell, if you have a cathode, you must have an anode, and both must be connected through an electrolyte. The concept is remaining same. You can see back side, this black color lead is connected. Let us see, maybe. Maybe even in this video you can see the black is there, which is occurring as an anode, and this is the rod inside the sponge is considered as a cathode. So this moves, releases gold, it just deposits. Okay. So the simple idea is this is the cathode part, and this is the cathode lead, which means the electron is rich here. So when we added some electrolyte inside this, there is a anode. From here, your particular gold ion travel through the cathode where it gets reduced. So current is flowing in the
Hello. Sir. Hello.
this video itself, I mean, your primarily your metal itself will not react. Before that, hydrogen and oxygen will just get into gas, and there won't be any water. It will become only salt. So this is the theoretical case. But zinc is the last metal.
Sir, excuse me, sir. Your screen is not visible.
Still, it is not visible.
Yes, sir. Your screen is not visible.
Okay. Now it is visible.
Yes, sir. It is visible now.
Yeah. Okay. So, so manganese is the last metal theoretically you can deposit. In practice, zinc is the last metal you can deposit because zinc's reduction potential is still negative, but before water splitting reaction. Okay. And almost all the other metals in positive direction, it is possible to deposit them by aqueous electroplating. So if I don't have a metal ion which is having the reduction potential less than 0.76, it is not possible to deposit in aqueous electrolyte. So then we have to go for some organic electrolyte, deprotic solvent, ionic liquid, etc. For example, people when they want to deposit aluminum, titanium, they use those kind of electrolytes. And you cannot do electroplating with very, very high electropositive metals like calcium, strontium, and all. Okay. So this manganese is the cutoff. Below that, you can deposit metal in metallic form from aqueous electrolyte. Beyond that, we have to go for non-aqueous electrolyte. Okay. So if you want to go for non-aqueous electrolyte, you have organic solvent, toluene, benzene. There are so many ether-based solvents, and there are ionic liquids. There are molten salt, and your typical organic solvents, as I was mentioning, like acetone, dimethyl sulfone, acetates. And only thing is organic solvents have a very, very limited conductivity because there is no conductivity at all because they are not that much polar. And whatever is polar also, again, corrosion is there because you have to handle organic solvent. Whereas in the case of your gold, silver, nickel, any other plating, you don't need that kind of electrolytes. Your simple water will do. Can maybe just to have a doubt, can anybody comment what is the electrolyte? What is the type of salt or electrolyte which we can use it for depositing gold? Because we all of you are chemists, right? There are different kind of electrolytes, right? Acidic, basic. What is the kind of electrolyte we use it for gold plating. Even in that video, they used that kind of electrolyte. Sulfate bath, chloride bath. What is the kind of if you name some common electrolyte name, what is a gold electrolyte name? That is used for gold, it is used for silver, all noble metals, that is the electrolyte which is used. Can somebody come on? We actually use cyanide-based electrolytes. Okay, so all your noble metal, if you want to get uniform coating, we use cyanide-based metal. If we don't use cyanide-based metal, I think screen is still visible, right?
Yes, sir.
Yeah, okay. So cyanide is what used, whereas in case of nickel, copper, other transition materials, we can use sulfate bath, acidic bath, etc. In, as I told, organic solvents have very poor conductivity. We typically go for ionic liquids. Ionic liquid is a very special solvent. We don't use every day. It is very costly also. But you can deposit any metal, calcium, lithium, whatever in the periodic table, whatever you saw here, up to lithium, it can be deposited in the ionic liquid. And you don't have to use water, and it is very having high conductivity, not like your organic solvent. Only drawback is very limited. Cost is going to be very big problem. So you cannot use for bulk application. Like if you go to any industry, because whenever it is saying electroplating, some of you may be having some idea what is this electroplating. We know whether we really use electroplating. Maybe just I will go some few slides ahead just to give you an idea. We will come back here. So this is a typical electroplated samples. Your Boeing, like whatever the unfortunate incident that happened in Ahmedabad recently. So many people were talking about safety, so many other things, right? So whoever has seen the video of a flight landing, you will see a single wheel that is coming to the front. That is called as landing gear. This is a typical look of a landing gear. It takes care of the entire weight of whatever hundreds or thousands of tons of your typical aircraft, and that single wheel is attached with a landing gear. Landing gear is a nickel chromium plated. The sample is shown here. It is typically like just like your shock absorber in a two-wheeler or in a cycle. So it once the load comes here, it just takes the load. So this is plated by nickel chromium. Inside also you have nickel chromium. You have some grease. So the primary idea is whenever there is going to be lubricant, whenever there is going to be thrust, this will take the load. It will go inside and it will provide the stability. That is the aim of a landing gear. Okay. Now this is where will be the landing gear. Fine. So now the typical home utensils, whatever we use, whether it is gold, silver, there are many people even today they eat with silver spoon. Okay, we talk the word born with silver spoon, right? The royal people, kings, they used to have silver spoon. People who cannot afford but who still have a lot of money go for silver or platinum spoon. Instead of pure metal, they go for plated metal. And this is your typical car wheel alloy and different components where gold is plated. Even your simple safety pin is also gold plated. So you can just think the variety. A safety pin which is not even 1 rupee, that is also gold plated with electroplating technique. The landing gear of a multi-crore this one aerospace equipment or a rocket or for that matter such a big passenger aircraft, that also is having this kind of electroplated compounds. And this is the typical different nuts and bolts which is plated with why we go for nickel or copper primaries, they don't get easily corroded. Whenever I want to have a
infrastructures and construction methods are also challenges. And then next one is durability and reliability concerns. That is, some smart materials degrade faster in India, diverse climate, extreme heat, humidity, or monsoons, materials like magnetological fluid may suffer from sedimentation or require complex magnetic field designs. And next one is the environmental and disposal issues. Here, certain smart materials contain rare earth elements or synthetic compounds that throws disposal challenges. Recycling and end-of-life management system are underdeveloped. And next one is a policy and regulatory gaps. There are no standardized guidelines for smart material use in public infrastructure or agriculture. Limited incentives or subsidy for adoption in rural or semi-urban areas is a biggest challenge. And next one is next we'll discuss the ways to overcome challenges of smart materials in India. That is, the first one is cost reduction through local manufacturing. Instead of importing expensive materials, we should use what we have in India, bamboo, clay, and laterite, to make smart materials. This will create jobs in villages and make these materials much cheaper for everyone to use. It will reduce dependency on imports and lowers cost for rural and semi-urban projects. And the next one is educational and skill development. Our colleges and technical institutes should teach students about smart materials through practical training. Even ITI students and workers should learn how to install and maintain these new materials properly. It will build a skilled workforce capable of designing, deploying, and maintaining smart systems. And then next one is public-private partnerships, that is PPP. That is, the government and private companies should work together to bring smart materials to people. Big companies like Tata and L&T can help government schemes reach more people effectively. Example, Smart City Mission, partnering with companies like Tata Projects and L&T for smart infrastructure. It will accelerate innovation and ensures quality implementation at scale. And the next one is policy support and incentives. Government should give financial help and quick approvals to make smart materials affordable for farmers and small builders. This will encourage more people to try these new technologies, like PM Kusum scheme, which supports solar-powered irrigation system using smart membranes. The impact will be making adoption financially viable for farmers and small builders. And next one is localized R&D and innovation hubs. Each region should have research centers that develop smart materials suitable for local weather and conditions. Kerala needs different solutions than Rajasthan because of climate differences. Example, bio-integrated design labs in Kerala and Gujarat working on algae-based walls and adaptive cooling. Tailoring solutions to local needs will encourage grassroots innovation. Our next one is a digital infrastructure expansion. Our next one is a digital infrastructure expansion. That is, modernized and digital infrastructure across the country needed for smart materials to work properly. When everything is connected, these materials can share information and work better together. Example, BharatNet project bringing high-speed broadband to over 250,000 gram panchayats. The impact is it enables real-time monitoring and integration of smart materials with IoT platforms. And the last overcoming challenges, that is community-led demonstration projects. Here, show people how smart materials actually work by creating model projects. When people see real benefits in their own community, they will trust and adapt these technologies. As discussed earlier, Bali in Jammu and Kashmir and Modira at Gujarat as a model for net zero and solar powered living. Our next one is a Government of India initiatives for smart materials. The first one is Clean Energy Material Initiative, that is CEMI. CEMI, that is Clean Energy Material Initiative. That is, it is launched by the Department of Science and Technology, that is DST. It is India's answer to making better batteries and solar panels. Our government is funding top researchers in IITs and national labs to develop materials that can store energy better and capture harmful carbon dioxide from the air. This means cheaper electricity and cleaner environmental for all of us. It focuses on R&D in materials for energy storage and solar cell, low energy semiconductors and carbon dioxide capture. It supports innovation in batteries, supercapacitors, hydrogen storage and fuel cell through allied research networks across IITs and national labs. And the second one is Samrat Udyog. Samrat means Smart Advanced Manufacturing and Rapid Transformation Hub. That is, it is managed by the Ministry of Heavy Industries. It is a Government of India initiative. Samrat aims to make our factories smarter by 2025. Instead of old-style manufacturing, factories will use robots, artificial intelligence, and smart materials that can change properties as needed. This will make our products better and create more jobs for tech-savvy workers. It builds an ecosystem for smart factories, automation, and digital twins by 2025. And the third Government of India initiatives for smart material, that is Material for Energy Conservation and Storage Platform, that is MECSP. MECSP, that is Materials for Energy Conservation and Storage Platform. MECSP is launched by the Department of Science and Technology. It has set up 4 special centers across India that work like energy labs. Scientists here are developing materials that can save electricity and store power for longer periods. This will help reduce our electricity bills and power cuts. It supports scalable technologies for energy conservation using advanced materials. And the next one is India Semiconductor Mission. It is launched by the Ministry of Electronics and IT. This is India's biggest push to make computer chips available locally instead of importing them from other countries with rupees 1.52 lakhs crore investment. We are building 5 major factories that will make chips with smart materials, reducing our dependence on foreign technology. And the last one is my Co-Innovate India platform. My Co is like a big idea competition where anyone like students, startups, or common citizens can suggest solution using smart materials for problems in their locality, whether it's clean water, better roads, or saving electricity. Good ideas get government support to become reality. It focuses on crowdsourcing innovation challenges, including smart material application in water, energy, and urban transformation. It engages startups and citizens in solving real-world problems using emerging technologies. Now, let us see a video to know how smart materials are being used in India.
Ma'am, the video is not audible.
Hello. Hello, ma'am.
The video is not audible.
Audible? Wait, ma'am. Wait. Hello, ma'am.
Yes,
Hello,
ma'am.
ma'am. Now it's audible, ma'am.
No, ma'am. Just
Wait.
play the video so that. Ma'am?
Ma'am. Wait, ma'am. Now it's working, ma'am. Hello, ma'am.
Ma'am.
Hello, ma'am.
Yes, ma'am, but
Okay. It's audible, ma'am.
no, ma'am, it is not audible, I guess.
Hello, ma'am.
No, ma'am, it is not audible, ma'am. Now
Okay,
also.
okay, ma'am. Huh?
It is not audible now.
Not audible now.
Oh, yes, ma'am. Maybe.
Hello, ma'am. Hello, ma'am. Hello. Sorry,
Yes,
there
ma'am.
is some audio issue. Sorry for that, ma'am.
No problem, no problem, ma'am.
Okay.
You can.
Water is supplied through cardboard boxes now. This video clearly shows how a small innovation with smart material can make a huge impact on the society and environment. Thank you. It's my duty to thank many people at this juncture. First, I thank my college chairman and managing director, principal, all the deans, and first year coordinators and HOD and my department friends for supporting and encouraging me continuously in all my endeavors. I am indebted to thank the dean and coordinators of Marthandam College of Engineering and Technology for providing me this opportunity to deliver my address on this interesting topic. I also thank Atal and AACT for providing such a platform to enable all the faculty to enrich their skills. I thank all the listeners for your patient listening. If you have any queries, please mail it to me, my mail ID appearing on this slide. Thank you. Thank you all, ma'am.
So thank you, ma'am. So participants, session all the sessions of this day has been ended. So if you have any questions to ma'am now, and you can also write up in the chat box also. Participants, if you have any queries, you can ask ma'am now. So we have come to the end of the session. So thank you, ma'am. So on behalf of the management, our respected principal, the organizing committee, and all the participants, I extend my heartfelt gratitude to our distinguished resource person, Dr. V. Swarnalatha, for delivering such an insightful and thoughtful session. Madam, the depth of your knowledge, the clarity of your explanation, and the practical perspectives you shared have truly enriched our understanding. Thank you so much, ma'am.
Thank you, ma'am. Thank you, ma'am.
So with this, The 6-day FTP program have come to an end. So I think you have the participants have got all the feedback link for the attendance, and I think you have filled all these forms already, and also the test you can attend the test. The test is available in your Atal website, and if you have any queries or doubt about the test, you can contact us. And also, after finishing a test, you have to fill the feedback which is given in the Atal page of your account, so that you can receive a certificate. So it is the instructions are given in the group also. You can go through it, and I think the test is open now. So, guys, go and check it out and try to attend the test now. If any interruption or something is available, you can contact us. You can do it now. I think the website is open now. You can go and check the your Atal web page now.
Good evening, madam. Hello, can you hear me?
Yes, sir.
Madam, can we take the test now?
Yes, sir. So after the vote of thanks, you can continue to take your test. Yes.
But in the portal,
Hello.
it's mentioned that one can start the test after 6:30 onwards.
Yes, sir. But the portal is open now. We have just checked out. So we can go to your Atal web page and check it.
Thank you.
So after the program, you can start your exam.
Okay, ma'am. Thank you.
Okay. So on behalf of our institution, Mathanam College of Engineering and Technology, I extend our sincere thanks to our distinguished resource persons for gracing this beautiful faculty development program and sharing their inspiring works and knowledge about all the topics what have they have taught us. A very special thanks to our respected principal for constant encouragement, leadership, and support, without which this program would not have been possible. And I also extend my thanks to the management, faculty colleagues, and the organizing committee members for their hard work, commitment, and seamless coordination in making this FDP a success. Last but not least, a big thank you to all the participants for your enthusiastic involvement and active contribution throughout the sessions. Your curiosity and interactions made the program lively and meaningful. Once again, I thank each and everyone who directly or indirectly contributed to the success of this 6-day faculty development program. Thank you all. So participants, you can start your exam now. And if you have any queries, please contact through the WhatsApp group. I think all the participants are available in the WhatsApp group, right? If anyone is not in the group, please text in the chat box so that we can give you the details through the WhatsApp.
அனைவருக்கும் மாலை வணக்கம். தீபம் படைப்பகம் கவியந்தன் சாரா அவர்களினுடைய பூ தீயாய் பூத்திருக்கு கவிதை விழாவிற்கு வருகை தந்திருக்கிற உங்கள் அத்தனை பேரையும் விழா குழுவினர் சார்பில் வருக வருக என்று வரவேற்று நாம் இப்பொழுது விழாவை துவங்குகிறோம். சிறப்பு விருந்தினர்களை நான் மேடைக்கு அன்போடு அழைக்கிறேன். முதலில் இந்த விழாவிற்கு நீங்கள் அழைப்பை ஏற்று வாழ்த்துறை வழங்க வந்திருக்கிற அமுதா தமிழ்நாடு அவர்களை உங்கள் கரவொலியோடு அன்போடு அழைக்கிறேன்.
Christy Edalarasi, participant, please mute your video audio. Christy Edalarasi. Actually, exam link is not available apart from the Atal web page. You have already applied in the FDP Atal web page, right? By using your username and password. So using your username and password, again log into the Atal website, and on the left side of the web page, when you open to your page, Atal web page, the left side there'll be many options. So on the left side, you can see assessment in that options. Among these options, you can choose the assessment, and when you click the assessment option, you'll be able to see a of our FDP, which with the number, application number, and the date, from the date which the Atal FDP has started, and the ending date, I think 18 August to 23 August. So at the end of the that column, you can see a blue color link. You can, when you choose that link, it will take you to the test. So you can finish your test by using that blue color link. So thank you all participants for your contribution, and you all the participants were so thoughtful, and you have asked your queries and interacted with all the resource persons. Thank you so much, participants. So with this, we end this FDP program. Thank you all. Dr. V. Kavita, can you contact me through the WhatsApp?